In this video, we are going to be discussing the fearful per unit method. To some engineers, the per unit method may feel or kind of seem like it's the non-dimensionalization techniques found in the physical sciences. Sciences like fluid dynamics, where things like characteristic units or dimensionless variables are used. Now, there might be similarities between per unit math and these other techniques, but it really is crucial to consider the per unit method for electrical engineering as its own discipline. In setting the boundaries for our discussion, we're going to talk about PE electrical applications for the per unit method. And so if you were going to go into the study of non-dimensionalization to understand the per unit method, it just is way too general, too big, and the specific application is just too remote to be an effective area of study. So let's just say the per unit method for the PE is its own thing. Well, what is the per unit method actually used for? Well, believe it or not, it's actually a simplifying technique. That's right, it's actually used to make things a lot simpler. Now, even though it may seem difficult or it may seem sort of scary or ambiguous, it's actually supposed to make your calculations simpler, easier, and actually a lot easier. So you shouldn't be scared of it. It's here to help you. It's your friend. And we're going to show you why you shouldn't be insecure at all about using it in your calculations. To demonstrate this, we'll take a look at a basic voltage drop problem. You see this simple circuit here, and at point A we are going to find the voltage. And this would be the relatively simple formula to use for that. It's really, in kind of a way you can look at it, it's like a couple of applications of Ohm's law. And really, what could be simpler than that? So here, to find the voltage at point A, we take our given voltage up here at the front, plus as well as the current, rather, and when we pass through the impedance values here, it's a simple Ohm's law voltage drop. Simple calculation, we do that again for this impedance. So two simple Ohm's laws going in sequence there to get to our final voltage in the end at point A. And that's it. Unfortunately, not all circuits are quite this simple. But if we take this pretty simple circuit that had a pretty simple application of Ohm's law to find voltage drop and add just one transformer, that's it, one circuit element to this very simple circuit, just one thing, you're going to see that the formulas and the calculations become really pretty incredibly more difficult. So here it is. Here's our simple circuit with just the transformer added to the middle. Should be pretty easy, right? Well, the first step maybe in this calculation is easy, which is on the primary side of the transformer, we're going to basically just do our Ohm's law calculation. Really not any different than our previous circuit analysis. We've done our pretty simple Ohm's law calculation, but now we've gotten to this transformer that we have to cross over and find the voltage on the other side. And in order to do that, we're going to have to do something with this turns ratio. And that something is this. So we've used these ends now in our second step to get the voltage on the secondary side of the transformer. We've crossed from primary to secondary using the turns ratio. But as soon as these ends get involved, we really see now that it gets significantly more complicated, because the remaining Ohm's law calculation we have to do on the secondary side is going to have to take into account these ends. We can't just let them go. We have to keep track of them. Now that we're on the secondary side, we have the voltage on the secondary side, we have this impedance that we've got to factor in for a second voltage drop, similar to our first example, our first step even. So our third step is voltage drop on the secondary side with this second impedance to find the voltage at A. And we're done. It's we can pat ourselves on the back. It's totally complete, right? Well, actually, we're not done. Because look at this I here. We've got to derive this I, that one, from the primary side current there. And in order to do that, we're going to have to, just like the voltage, use our turns ratio. As I'm writing the formula for this, one quick thing to notice above is when we used the turns ratio to convert the voltage from the primary to the secondary, the numerator was primary and the denominator was secondary, and it matched the ends in the turns ratio. But for the current, notice here it's flipped. We've got the secondary in the numerator and the primary in the denominator, but the ends for the turn ratio remain the same. And that's an easy little thing to forget on a test and get an incorrect answer. And this is our step 4. So now technically this would be enough information to solve for voltage at point A. But if you notice the V2T up here in the formula up here, it was derived. And so we're going to, as this final step, really show one sort of final complete formula that captures all of this spelled out. Let's analyze this formula in sort of step-by-step fashion at the end here. So our first step in this final formula is this V2 is now sort of spelled out, derived from this section here. It was applied by taking this part here and taking it from here up there. And you see how it gets applied exactly this section here. And for this last section, there were no intermediary variables required, so it's just spelled. It's the same formula, section of the formula here as it is here. Taking a quick comparison now from our first very simple circuit and the voltage drop problem associated with that to our second one with the transformer added, you see that it becomes much more complex with just one transformer added. Now, in practical, normal engineering situations, you're going to have circuits with multiple transformers on them. Now, just imagine with multiple transformers how out of control the ends are going to be and how difficult it's going to be to keep track of all of that information. You're going to need a tool to manage that amount of data to be worked with. So that's where the per unit is going to come into play. It is a tool to manage all of this extra information that is added by these circuit elements. Now, a quick note about the PE. The PE may not ask you questions with multiple transformers or multiple circuit elements like this, even though you're likely to see that in practical engineering applications. But from the practical engineering applications of having multiple transformers and needing to use the per unit method to manage that, the PE is going to hit on your knowledge of the per unit and just provide you with a little more simplified example, but still require you to know the interworkings and the mechanism of per unit methodology. It's shorter and it's simplified, but it's still per unit calculations on it. So what we've seen in this video is that the turns ratios of transformers create massive complications in our circuit analysis, and that it is exactly at that place that the per unit method finds its application. It is applied in order to simplify the complications created by turns ratios in transformers.